Okay, so thank you. I will try to keep the last talk of the session concise. And the talk will be focused on classical gauge theories. And namely, I will discuss different kind of variables that one can introduce to deal with gauge theories. And this description is inspired by the embedding manifold, by the embedding approach to Riemann manifolds. So I will just recall what one does in the standard approach. There are those theories. Of course, one has some n-component field and the gauge potentials which take values in the Lie algebra of the gauge group UN. One defines the covariant derivative, and the field strength is the commutator of covariant derivatives. And this is what we do usually, of course. And my talk basically relies on this fact equation 3, that this equation has a solution for the quantity V, which is a rectangular matrix valued, let's say, field that has little n coulombs and capital N rows. So for n large enough and any potential a mu, one can find such a matrix valued function. And this V essentially, it gathers a little n tuple of orthogonal vectors, which are vectors in the capital N dimensional complex space. And yeah, so this goes under the name universal connections, and it was showed in the 60s. So I will proceed as follows. I will first recall what one does with embedded manifolds, embedded Riemann manifolds, namely the approach using the so-called shape operator, which is essentially the extrinsic curvature. And then from the lessons learned, I will move on to how one can use those insights in the realm of Yang-Mills theories. And I will provide some examples, simple examples from electromagnetism. So let's say we have a d-dimensional manifold, which is embedded in a capital N dimensional flat space. And this embedding gives us tangent space at each point of the manifold, or let's say it gives us a projector on this tangent space at each point, and the respective projector on the normal space. And these projectors, they change as we move along the manifold. And knowingly, in the standard approach to covariant derivatives on embedded manifolds, one takes a vector field, one differentiates partially, and then projects the result, and one does it for the tangent part and the normal part separately. Yeah, so one can write, in fact, this description in a way that mirrors the connection kind of prescription for covariant derivatives, where we have this quantity S mu. This is what is called the shape operator. It is really just essentially the second fundamental form of the embedded manifold, or the extrinsic curvature, as people call it. So the formula for this is equation 5. It can be written concisely with the use of this reflection operator. So the R is a reflection with respect to the tangent plane. And yeah, so it's just convenient to write it in this form, in fact. So basically what describes the geometry of the embedded manifold is the way how the tangent plane rotates as we move along the manifold. And so it's a tangent, it's a subspace of the capital N dimensional flat space. And I will refer to it as a rotating blade, so it's some kind of blade that moves, that rotates as we move along the manifold. And it can be represented analytically either by the projector or the reflection. Now, since S is given by this derivative of the rotating blade, it satisfies some differential identity, this one. And when we calculate the curvature of the connection, we can express it in terms of the commutator of this shape operator. So we don't need the derivatives of these connection coefficients. So this is well known for embedded manifolds. So the extrinsic curvature gives us, by a commutator it gives us this total curvature omega, and once we project this omega to when we separate the tangent part of this total curvature, we get the intrinsic Riemann square. So the lesson would be that although one usually uses the intrinsic description of things, well, in the intrinsic treatment, we need for the Christoffel symbols, we need derivatives of the Christoffel symbols and the commutator of them to get to the curvature. So now let's try to go to Young's theories and basically do kind of a reverse procedure. So the usual exposition of the Young's theories, I would think of it as an intrinsic description of the bundle, which has this U little n gauge group, and we have this covariant derivative. We know that we can find the rectangular matrix V such that 7 is fulfilled. So we basically are going to develop some kind of embedded picture for this this traditional Young's theory. So this V defines. So V is an n-tuple of orthogonal vectors. So it gives us some subspace of the capital n-dimensional complex space together with a choice of orthogonal bases in that space. And if we only look at the projector on that space, we can write it as V dagger. And this is the subspace that is spanned by the coulombs of the rectangular matrix V. And we can define this ambient big covariant derivative in analogy with the embedded manifolds approach. Indeed, using this projector P, and we define the shape operator for the Young's theory, essentially, because this is defined in terms of the R, which is the reflection operator, which is given in terms of the projection operator, and the projector is given in terms of this matrix V. So we know that we can move from the traditional connection coefficients description to the description using essentially the rotating blade. And now when we calculate the curvature, things go the same way as for the Riemann manifolds. We can write them in all sorts of different ways. So it's a commutator of the shape operator, or it's a commutator of the first derivatives of the rotating blade. And so now let's look crucially at what are these original gauge transformations? What do they do in our picture now? So the original gauge transformations of the U little n gauge group, so what the like intrinsic gauge group, let's call it U. So there are local gauge transformations. They transform the field like as usual, the connection as usual, and the field strength as usual. And quite naturally, they act on this matrix B from the right, as U dagger. Essentially, they scramble the columns of the matrix, so they rotate the bases within that subspace, in that rotating blade. But okay, so this is what it has to be, but the quantities, but the subspace is preserved by this operation, and the same holds for the quantities that are derived from this. So the projection of this rotating blade, the shape operator doesn't see the gauge transformations. So we kind of get rid of this gauge invariant because it is because the new quantities are manifestly gauge invariant. There's no gauge freedom. Or there is, but it's trivial. It doesn't do anything to the subspace. It only rotates the basis. But if we don't even choose the basis, then we just have no notion of the gauge structure. So yeah. So time is coming. Let me show some examples. So just to show that the thing is real, like we have electromagnetism, which is U1 theory, and let's pick this capital N to be 2. So this is not enough to represent all possible gauge potentials, but it is good enough to represent for some interesting examples. So we can parameterize this rectangular matrix V like this, so it only has to be normalized to 1. Basically, it's a vector. So we have some local parameters, alpha, beta, and rho, the rotating blade, and calculated looks like this. And the equation for V, so that's the original equation on the first slide, just written in terms of these parameters, alpha, beta, rho, not this form. And yeah, so let's take a say electromagnetic wave for the full potential, and one can solve those equations and find alpha, beta, rho look like this, and the rotating blade is something like this. So it's a function of x which takes values in, well, it's in the so-called Grassmannian manifold of little n-dimensional subspaces in the capital n-dimensional space. So now another example which is more interesting is the magnetic monopole. So it's a configuration of the electromagnetic field where the electric field is 0, magnetic field is central, radial, and it is well known that in order to describe it, when it's two patches which overlap and the gauge potentials in the traditional approach, they have to be defined. We need two gauge potentials defined on each of those patches separately, and on the overlap of the patches, the gauge potentials are related by gauge transformation. And so one of the potentials is not defined for positive z-axis, the other is not defined on the negative z-axis, something like this. So that's the monopole bundle. And we can find again the quantities alpha, beta, and rho at each of those patches, and also on the overlap, well, for A plus or A minus separately. And we find that the rotating blade is just the same with respect to both of these patches on the overlap, which is not a big surprise, because as we said, the rotating blade doesn't see the gauge transformation at all. So it's just, it's given, it's not altered by the gauge transformation that transforms from A plus to A minus. Yeah. So I think totally. Okay, so I showed a way how to maybe use different variables instead of those that we are very familiar with and use every day. That in principle this can be done. And the question is whether it's a useful thing. So there are some hints that it might be useful, because this intrinsic gauge invariance is not present. It's not a problem anymore. Well, what we have to deal with quantities that are like, this R is well, we need some more differential geometry, because it's a matrix in the end, reflection matrix that changes as we move along the manifold. So I will just end with a quote of David Hessener, whose work was very inspirational for this, so that the treatment of intrinsic geometry can be simplified by coordinating with extrinsic geometry. So he wrote this when studying embedded Riemann manifolds, but I just want to I just try to argue that this could be pertinent also for Janus theories. Yeah, that's all.
We have time for final short question. There's one question.
Thank you for a lovely talk. May I ask a very simple question? Why is it called rotating blade?
Because it looks like a blade, I would say. Well, this has Spanish kind of terminology. So the blade, well, it's a subspace in a bigger space, so why not a blade? Yeah. And it's rotating because I would say that as you move on the manifold, it changes. Yeah, so it's.
Would you accept the more fun name moving mirror? Because it's a reflection.
It's a reflection operator, so why not call it moving mirror or manifold mirror?
Yeah, that would be even more obscure.
Okay, so let us thank the speaker again.